Tonight, we're going to look at where we actually live in this galaxy. The full, three-dimensional structure that contains us on a galactic scale. It's called the Orion Arm. Every star you've ever seen with the naked eye is inside it. Every planet we've ever visited, every probe we've ever launched, every telescope image we've ever taken of something we called close, all of it comes from the same structure. Most people know we live in the Milky Way, but almost nobody thinks about what part of it we're in, or the true scale of it. By the end of tonight, you're going to see just how vast this structure really is, and just how small we are inside it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Milky Way is a barred spiral galaxy. That's the formal classification, and it means something precise. At the center sits a dense, elongated bar of stars, stretching roughly 27,000 light-years from end to end. From the ends of that bar, spiral arms unwind outward, like water spinning off a wheel. These arms are not solid structures. They're not walls or tubes of material floating in space. They're regions of higher density, zones where stars, gas, and dust are more tightly packed than in the gaps between them. Think of it less like the arms of a starfish and more like the bands in a whirlpool, regions where material slows down and piles up as it moves through. The Milky Way has 4 major arms. They're named Perseus, Norma, Scutum Centaurus, and Carina Sagittarius. Each one is a primary structural feature of the galaxy, stretching for tens of thousands of light-years, containing billions of stars, and reaching from near the galactic center out toward the outer edge of the disk. And then there are the minor arms, smaller spurs and bridges that branch off from the major ones. We live in one of those. The Orion Arm, sometimes called the Orion Spur, or the local arm, is a partial arm of the Milky Way. It branches off from the inner edge of the Perseus Arm and extends outward at a slight angle, threading through a region roughly halfway between the galactic center and the outer rim. We sit inside it. Our entire solar system, every planet, every moon, every asteroid and comet and spacecraft we've ever launched, all of it is embedded in this spiral feature, roughly 26,000 light-years from the galactic center. For most of the 20th century, astronomers classified the Orion Arm as genuinely minor, a small spur, a modest connecting bridge between 2 larger arms. Not a real arm in its own right. That picture has changed dramatically in the last decade. New data from missions like Gaia, the European Space Agency's Space Observatory, that has been mapping the positions and motions of stars across the Milky Way with extraordinary precision, has revealed that the Orion Arm is far larger, far longer, and far more structured than anyone previously thought. We're not living in a cosmic backwater. The revised picture puts the Orion Arm at somewhere between 10,000 and 25,000 light-years in length, possibly longer. Its width spans several thousand light-years. It contains an enormous number of young stars, active star-forming regions, and massive molecular clouds where new stars are still being born right now. It is a substantial structure in its own right, just not classified as one of the 4 main arms because it doesn't extend from the galactic bar outward in the way they do. The name itself tells you where we got our first clue about it. The constellation Orion. When you go outside on a clear winter night in the northern hemisphere and look toward Orion, you're looking in the direction of some of the Orion Arm's most dramatic features. That distinctive pattern of stars, the three-star belt, the bright blue-white supergiant Rigel at one corner, the red supergiant Betelgeuse at the other. The fuzzy smudge just below the belt that you might mistake for a dim star at first glance. All of it is embedded in or directly associated with the Orion Arm. That fuzzy smudge is the Orion Nebula. It sits roughly 1,340 light-years from Earth, close in galactic terms. The Orion Nebula is one of the most active star-forming regions in our galactic neighborhood, a churning cloud of gas and dust, roughly 24 light-years across, where gravity is currently pulling material together into new stars. Some of those stars are already forming. Some already have protoplanetary disks, rings of gas and dust swirling around newborn stars where planets may be assembling at this moment. When astronomers point the James Webb Space Telescope at the Orion Nebula, they see something that takes a moment to fully absorb. They see the process of solar system formation happening in near real time. The light we're receiving left the nebula around 13 centuries ago, but the physics hasn't changed. New suns are switching on in that cloud right now. The Orion Nebula is not a relic. It's a factory. And it's one of the reasons the Orion Arm gets its name. It's the defining landmark of the arm, as seen from Earth, the most dramatically visible feature of the local galactic structure when you look up at night. But the Orion Nebula is just one feature. The arm stretches in both directions from our position, filling a region of space that contains thousands of stellar nurseries, tens of thousands of young massive stars, and more raw material yet to be processed into new suns than exists in most parts of the galaxy outside the primary arms. To understand the true scale of the Orion Arm, you have to start with the unit astronomers use for these distances: light years. 1 light year is the distance light travels in a single year at its full speed of about 186,000 miles per second. That works out to roughly 5.9 trillion miles. The Orion Arm, at its revised estimated length of somewhere around 25,000 light-years, is therefore on the order of 150 quadrillion miles long. That number is effectively meaningless when spoken out loud. No human brain evolved to process scales like that, and it would be dishonest to pretend that simply hearing it creates any real understanding. So, instead, think about it in terms of time. The fastest spacecraft currently traveling away from Earth is Voyager 1, moving at roughly 38,000 miles per hour. At that speed, to cross the Orion Arm from one end to the other would take roughly 450 million years. That's 450 million years of continuous travel at the speed of the fastest spacecraft currently leaving our solar system. And the Orion Arm, let me be clear, is not a major arm of the Milky Way. The Perseus Arm, one of the two dominant arms, stretches roughly 65,000 light-years. The full diameter of the Milky Way's disk is somewhere around 100,000 light-years across, with some estimates pushing further. The Orion Arm is a feature inside that system, and crossing it at Voyager's speed would take the entirety of the Cambrian explosion to the present day, with time to spare. That is the scale of where we live. Not the scale of the universe. Not the scale of the observable cosmos, which stretches about 93 billion light-years across. Just the scale of the arm we live in. Just our local portion of one galaxy. Now let's look at what actually fills that space. Because the scale only becomes real when you understand what's in it. Stars, primarily. The Orion Arm contains billions of stars. They range from massive blue giants burning through their fuel in just a few million years to dim red dwarfs that will keep quietly fusing hydrogen for hundreds of billions of years, long after the Sun has expanded and cooled and gone dark. The Sun itself is an average star, not particularly large or small, not particularly young or old. It sits about 4.6 billion years into its estimated 10 billion year main sequence lifespan, classified as a G-type main sequence star, sometimes called a yellow dwarf, though from space it would appear white rather than yellow. Its luminosity is 1 by definition. Every other star gets measured against it. When you look at a star and see it's 10 times more luminous than the Sun, that means it's releasing 10 times as much energy per second into the surrounding space. In the Orion Arm, you can find stars millions of times more luminous than the Sun. Stars like Eta Carinae, which sits roughly 7,500 light-years away in the Carina region at the far end of the arm. Eta Carinae is a stellar monster. It contains somewhere between 100 and 150 times the mass of the Sun crammed into a single gravitationally bound object. It's burning through its fuel at such an extreme rate that it's expected to end its life in a hypernova, a kind of explosion far more energetic than a standard supernova, at some point in the next few 100,000 years. When it does, the burst of radiation it releases will be detectable from Earth, even at a distance of 7,500 light-years. Not dangerous to us, but measurable. Eta Carinae already had a major outburst in the 1840s that briefly made it the second brightest star in the night sky, visible in daylight, without actually triggering a supernova. That was a near miss on a catastrophic scale. It shed mass equivalent to several times the mass of our Sun in the span of a few years. The material it ejected is still visible today as the Homunculus Nebula, a dumbbell-shaped cloud of gas and dust surrounding the star, expanding outward at about 400 miles per second. And Eta Carinae is still there, still unstable, still building toward an ending that will be one of the most violent events in the local galaxy when it finally arrives. The Orion Arm contains dozens of objects in states of dramatic instability, massive stars in the final phases of their lives, burning too hot and too bright to survive long by cosmic standards. And thousands more that haven't quite reached that stage yet, blue and blue-white supergiants, still in what passes for the prime of their short, intense lives, pouring out ultraviolet radiation that would be lethal to any unprotected biology within a few light years of them. This is the neighborhood, not a gentle, stable zone of quiet suns. A region filled with stellar extremes, from the smallest dim red dwarfs you'd need a telescope to detect to the largest and most violent stars in the local galaxy. Both extremes coexist in the same arm, at different distances, in very different parts of its length, but part of the same structure. One of the most important recent revelations about the Orion Arm is the recognition of how much internal structure it actually has. It's not a uniform band of material. It contains distinct concentrations of star formation grouped into recognizable regions, connected by filaments of gas and dust, separated by zones of relative emptiness. Astronomers have mapped several major star-forming complexes within the arm. The Orion Molecular Cloud Complex, the closest large star-forming region to our solar system, spans hundreds of light-years and contains the Orion Nebula as just one component of a much larger system. Within this complex, there are multiple distinct clouds at different distances and in different stages of evolution. The Orion A cloud contains the Orion Nebula and the dense stellar nursery behind it. The Orion B cloud, slightly further away, contains a different collection of young stars and protostars. Further out in the arm, there's the Ophiuchus star-forming region, roughly 450 light-years from Earth, where protostars are still collapsing from clouds of molecular hydrogen. The Ophiuchus complex is a darker, quieter kind of star formation than Orion. It's mostly making lower-mass stars rather than massive blue giants. But it's still actively manufacturing new suns from raw material, right now, at a distance of 450 light-years from where you're sitting. The Perseus molecular cloud sits roughly 1,000 light-years out, a dense concentration of gas where dozens of young stellar objects are currently in various stages of formation, some just beginning to condense, some already hot enough to be visible in infrared, some surrounded by disks that may form planets within the next million years. The Taurus molecular cloud, roughly 450 light-years distant, is one of the nearest active star-forming regions to the solar system. It's quieter than Orion, forming lower-mass stars, but it's still producing new suns from the same basic ingredients: hydrogen gas, dust grains, and gravity. All of these regions are features of the Orion arm. All of them are active, ongoing, dynamic. And all of them are visible, at least to our instruments, from the surface of a small rocky planet sitting quietly inside the arm that contains them. The Milky Way takes about 225 million years to complete one full rotation, one orbit of the galactic center. That period of time is called a galactic year, or sometimes a cosmic year. Our solar system has orbited the galactic center roughly 20 times since it formed. In one galactic year, the entire configuration of the spiral arms changes substantially. Stars that are currently inside the Orion arm won't be in it the same way a galactic year from now. This is because spiral arms are not made of fixed stars moving as a group. They're more like a traffic jam. Picture a busy highway where cars slow down near an obstacle. The jam appears to have a fixed location, even though the individual cars are always moving through it. New cars arrive from behind, slow down, pass through, and continue on the other side. The jam persists, even though it's never made of the same cars. Spiral arms work similarly. They're density waves, regions where gravity causes material to pile up and slow down as it passes through, making those regions appear brighter and more active, even as the individual stars inside them constantly drift in and out. The Sun is currently passing through the Orion arm at a relative velocity of a few miles per second compared to the arm's average motion. It has spent time in the arm. It will eventually drift out of it, and over billions of years, it will pass through multiple spiral arms as it continues orbiting the galactic center. The encounter between a solar system and a spiral arm has physical consequences. When the Sun passes through denser regions, it encounters more material, more stellar neighbors, and potentially more disruptions to the distant cloud of comets that surrounds the solar system. This outer reservoir of comets, called the Oort cloud, extends roughly a light-year from the Sun in every direction and contains trillions of icy objects left over from the formation of the solar system. Most of those objects will never come near the inner solar system. But gravitational disturbances, whether from passing stars or from the denser material in a spiral arm, can nudge Oort cloud objects onto new paths, sending some of them plunging inward toward the planets. Some researchers have proposed that periodic increases in comet impacts on Earth may correlate with the Sun's passages through denser parts of the galaxy. The idea is not definitively established. The geological and fossil record is complex enough that drawing precise timing correlations is difficult. But the basic physics is real. Our position in the galaxy, even our specific position within the Orion Arm, is not simply a geographic fact. It may be part of a longer story about what life on Earth has experienced over billions of years. Where we happen to be in the Arm, relative to its densest regions and most active stellar complexes, has potentially shaped the history of the planet we live on in ways we're only beginning to piece together. The local bubble is one of the stranger features of our immediate galactic neighborhood, and most people have never heard of it. Our solar system doesn't sit in a typical region of the interstellar medium. We're inside a large, irregular cavity in the gas of the Orion Arm, a region where the density of interstellar material is substantially lower than in the surrounding areas. This cavity is called the local bubble. It spans roughly 1,000 light-years in its longest dimension, though the shape is irregular and its boundaries are gradual rather than sharp. The interior of the local bubble is filled with hot, thin plasma heated to temperatures of roughly 1,000,000 degrees. That sounds extreme. It is extreme. But this hot gas is also extraordinarily tenuous. There's so little material inside the bubble that despite its temperature, it carries almost no actual thermal energy by any human measure. The individual atoms are moving fast, as hot atoms do, but there are so few of them that they barely interact with anything. Temperature and heat are different things when densities are this low. The local bubble is thought to have been carved out by a series of supernova explosions over the past several million years. When a massive star ends its life in a supernova, the explosion releases an enormous amount of energy, blasting an expanding bubble of hot gas outward into the surrounding medium. Multiple supernovae in the same general region can create overlapping bubbles that merge into a single large cavity. Astronomers have traced the origin of the local bubble to a group of massive stars that lived and expired in this region over the past 10 to 20 million years. Their remnants, the neutron stars and black holes they left behind, have drifted away. But the cavity they carved is still here, and we're inside it. A study published in 2022 in the journal Nature used Gaia data to map the star-forming regions around the edge of the local bubble in striking detail. The researchers found something that, once you see it, is hard to unsee. Nearly every nearby molecular cloud, every active star-forming region within roughly 1,000 light-years of us, sits on or near the surface of the local bubble. The Taurus clouds, the Perseus clouds, the Ophiuchus region, clouds near the southern coal sack. All of them appear to lie along the expanding shell of material that the ancient supernovae pushed outward over millions of years. The researchers traced this shell's expansion back to its origin point and timing, concluding that the local bubble began expanding about 14 million years ago, driven by roughly 15 supernovae over that period. That sequence of ancient stellar explosions didn't just carve out the cavity we currently inhabit. It compressed the surrounding gas into dense shells that are now actively forming new stars, including the star-forming regions that were observable when modern humans first appeared on Earth, including regions that are still actively making new stars right now. The ancient deaths of massive stars, millions of years before our species existed, triggered the births of stars that are igniting at this moment. And we're living inside the bubble those deaths created. Understanding where we are inside the Milky Way required solving what turned out to be a genuinely difficult problem. You can't step outside the galaxy and look back at it. You're embedded in it. Trying to map the Milky Way's spiral structure from inside is like trying to map a city while standing blindfolded in the middle of a crowded park. You can tell there are buildings around you. You can tell some are close and some are distant. But seeing the full layout, the streets, the districts, the overall shape is extremely hard when you can't get above it to see the pattern. For most of the 20th century, astronomers used different wavelengths of light to try to peer through the dust of the Milky Way and trace its structure. Visible light gets blocked by interstellar dust relatively easily. The dust grains scattered through the disk absorb and scatter visible photons, which is why the band of the Milky Way you see in a dark sky location looks dense and cloudy rather than perfectly transparent. But radio waves pass through dust almost unimpeded. In the 1950s, astronomers used radio telescopes to map the distribution of neutral hydrogen gas in the Milky Way by detecting its characteristic emission at a wavelength of 21 centimeters. Hydrogen emits this specific wavelength when the spin of its single electron flips relative to its proton. It happens rarely for any individual atom, but hydrogen is so abundant that the cumulative signal is detectable across vast distances. This technique revealed the broad outlines of spiral structure in the Milky Way for the first time. Astronomers could see regions of higher gas density corresponding to spiral arms. They could trace the arms across the galaxy, or at least the portions visible from Earth. But the mapping was imprecise. The velocities of gas clouds told you their distance only if you made assumptions about how the galaxy rotates, assumptions that turned out to be not quite accurate in all directions. Infrared observations improved things considerably. Infrared light penetrates dust better than visible light, and by the 1990s and 2000s, infrared space telescopes were revealing star clusters and massive stars embedded deep in the disk that visible light surveys had missed entirely. The Spitzer Space Telescope, launched in 2003, conducted a major survey of the Milky Way in infrared wavelengths and produced detailed maps of the stellar populations in both the disk and the spiral arms. From Spitzer data, astronomers began to pin down the positions of the four major arms with more confidence. They could see star clusters that were previously invisible, massive young stellar objects hidden behind curtains of dust, and the overall shape of the disk with unprecedented clarity. But the real transformation came from astrometry. The precise measurement of the positions and motions of individual stars. The Gaia mission, launched by the European Space Agency in December 2013, was designed specifically for this purpose. Gaia measures the positions, distances, and motions of stars across the Milky Way with a precision that previous instruments couldn't approach. It does this using parallax, the apparent shift in a star's position as Earth moves around the Sun. When you hold your finger up in front of your face and close one eye, then the other, your finger appears to jump relative to the background. That's parallax. Stars are far enough away that the effect is tiny, but measurable if your instruments are good enough. Gaia's instruments are extraordinarily good. Its first major data release covered over 1 billion stars. Its subsequent releases added more, with improving precision at each step. The third major data release, in 2022, provided positions, distances, and motions for nearly 1.5 billion stars, reaching out to thousands of light-years in multiple directions with errors small enough to be scientifically meaningful. The effect on our picture of the Orion Arm was substantial. Previous estimates had the arm as a modest spur, a few thousand light-years long. Gaia revealed coherent features, stretching many times that distance. The arm's physical extent and its width were both revised sharply upward. A study using Gaia data combined with observations of masers, compact sources of radio emission associated with massive star-forming regions, traced the Orion Arm's structure across a baseline much longer than previously possible. The arm emerged from that analysis not as a minor connecting bridge, but as a substantial galactic structure in its own right. The fact that we spent most of the 20th century thinking we lived in something smaller says less about the arm and more about how hard the galaxy is to map from the inside. We were wrong. The neighborhood was bigger than we thought. It still is. The arm is filled with objects that reward, looking at individually, not just as statistics in a census. The Rosette Nebula sits about 5,200 light-years away in the constellation Monoceros. It's a ring-shaped cloud of glowing gas, about 130 light-years across, surrounding a young open star cluster at its center. The hot young stars in that central cluster are bombarding the surrounding gas with ultraviolet radiation, stripping electrons from hydrogen atoms and causing the cloud to glow in the characteristic deep red of ionized hydrogen. The rosette looks delicate when imaged from our distance. Up close, it's a violent place. The radiation from those central stars is so intense that it's actively carving away the surrounding cloud, driving stellar winds that sculpt the gas into intricate pillars and filaments before eventually dispersing it entirely. In a few million years, the rosette will be gone. The gas it's made of will either have condensed into new stars or been blown out into the interstellar medium. The cluster at its center will remain, drifting through the arm as its stars age and eventually spread apart. The Carina Nebula is one of the most dramatic features in the Orion Arm. It sits roughly 7,500 light-years away and spans about 300 light-years, making it larger than the Orion Nebula, despite being nearly 6 times more distant. The Carina Nebula contains some of the most massive and luminous stars known anywhere in the Milky Way, including Eta Carinae. It also contains the cluster NGC 3372, with dozens of O-type stars, the hottest and most massive stellar classification, pouring energy into the surrounding nebula at rates that reshape the gas over timescales of thousands of years. The James Webb Space Telescope has imaged the edge of the Carina Nebula in extraordinary detail, revealing dozens of previously unknown protostars and jets of material erupting from newly forming stellar systems. Star formation happening on a scale that dwarfs the Orion Nebula entirely. There's the Eagle Nebula, 6,500 light-years away, home to what is arguably the most famous image in the history of astronomy, the Pillars of Creation. The pillars are columns of dense gas and dust, each several light-years tall, that have been sculpted by the radiation and stellar winds from a young star cluster called NGC 6611 nearby. Hubble imaged them in 1995 and produced one of those photographs that entered the cultural consciousness so completely that anyone who's spent time thinking about space has seen it. The James Webb Space Telescope imaged them again in 2022 in infrared, revealing details invisible to Hubble, including newly forming stars embedded within the pillars themselves. The pillars are being eroded. The radiation from the hot stars nearby is slowly destroying them from the outside in. In roughly 100,000 years, the pillars will no longer exist. But the protostars forming inside them right now, if they complete their formation before the pillars dissolve, will survive and become part of the galaxy for billions of years. The pillars are making stars, even as they're being taken apart. There's the Lagoon Nebula, about 4,100 light-years away in Sagittarius, one of the few emission nebulae visible to the naked eye from a dark location. There's the Trifid Nebula nearby, roughly 9,000 light-years distant, unusual for its combination of emission, reflection, and dark nebula regions in the same object. There's the Omega Nebula, also called the Swan Nebula, at roughly 5,000 to 6,000 light-years, one of the most massive star-forming regions in the Milky Way. The Omega Nebula contains enough raw material to produce several thousand stars the size of the Sun. It's actively doing so. Each of these objects is a feature of the Orion Arm. Each one is active, dynamic, physically extreme in its own way. And each one is visible in principle, at least with the right instruments, from the surface of a small rocky planet sitting quietly inside the arm that contains them all. The Sun's position within the Orion Arm is not arbitrary from a habitability standpoint. Not that we chose it. We didn't. We're here because the processes that formed the solar system 4.5 billion years ago happened here. The particular cloud of gas and dust that collapsed to form the Sun and its planets was in this part of the arm at that time, and that's where we ended up. But the position turns out to have properties that may matter for a planet trying to sustain complex life over billions of years. We sit in a relatively quiet region of the arm, not inside a dense, active star-forming complex where intense radiation from nearby massive stars would bathe the solar system in levels of ultraviolet and X-ray energy that could make the surface of a planet deeply hostile. Not close to the galactic center, where stellar densities are so high that gravitational interactions between neighboring systems would frequently disrupt stable planetary orbits. Not in the outer edge of the galaxy, where the interstellar medium is so thin that the raw material for rocky planets, the elements heavier than hydrogen and helium that were forged and scattered by billions of years of previous stellar generations, would be too sparse to build Earth-like worlds. We're in a middle zone, far enough from the center to be in a relatively calm region where stellar encounters are rare, close enough to the center that the gas from which we formed had been processed through multiple previous generations of stars and was enriched with carbon, oxygen, nitrogen, silicon, iron, and all the other elements that make complex chemistry and rocky planets possible. The concept of a galactic habitable zone was formalized in the early 2000s. The idea is that a galaxy has a region, analogous to the habitable zone, around an individual star, where the conditions for complex life are most favorable. Too close to the galactic center means too much radiation, too many stellar encounters, too many nearby supernova events. Too far out means too few heavy elements and too sparse an environment. The Orion Arm sits in the proposed galactic habitable zone. Whether this constraint matters as much as the original models suggested is debated. More recent research suggests the galactic habitable zone may be broader than initially thought, that the inner boundary may not be as harsh as feared, and that life, if it exists elsewhere in the galaxy, may be more tolerant of a range of galactic environments than early models assumed. But the basic observation remains. We're in a part of the galaxy that isn't obviously hostile to the existence of complex chemistry and long-term planetary stability. The universe is mostly places where such conditions don't apply. The interior of a star, the surface of a neutron star. The interior of a molecular cloud, too cold and dense for anything but the simplest chemistry. The vast regions between galaxies where the density of matter is effectively zero. That we happen to be in a place where the temperature, density, radiation environment, and elemental composition are all within ranges compatible with biological complexity is a significant fact about our position in the cosmos, even if it's a fact we had no say in. The nearest stars to our Sun all sit within the Orion Arm. Proxima Centauri, the closest, is about 4.24 light-years away. That's roughly 25 trillion miles. It is, in every practical and engineering sense, unreachably far with any technology we currently possess or could build in the near future. Alpha Centauri A and B, the two Sun-like stars that make up the other members of the nearest star system, orbit each other at a distance that varies between roughly 11 and 36 astronomical units, and lie at essentially the same distance as Proxima. Barnard's star, a red dwarf about 6 light-years away, is the next nearest individual stellar system. Wolf 359, Lalande 21185. Sirius, the brightest star in the night sky, at about 8.6 light-years. Epsilon, Eridani, and Tau Ceti, which have long been of interest to astronomers looking for potentially habitable planetary systems. All within a few dozen light-years. All inside the Orion Arm. All separated from our Sun by distances so enormous that our fastest spacecraft would take tens of thousands of years to reach the nearest of them. And Proxima Centauri, the closest star we know of, is simply another point in the arm. Not the edge of the arm. Not a distant outpost. Just a neighbor in the same local region of the same galactic structure. The stars, within about 325 light-years of the Sun, constitute what astronomers call the local stellar neighborhood. This region contains roughly 3,000 to 4,000 stars. Most of them are red dwarfs, dim and small, many probably hosting planets, almost none of them visible to the naked eye from Earth. Of those several thousand stars, only a handful are large and luminous enough to be detected without a telescope. The rest are invisible to unaided human vision. This matters more than it might seem. When you look up at the night sky and count stars, you might see 2,000 on a clear night from a reasonably dark location. All of those visible stars are within roughly a few thousand light-years. They're the bright, luminous, often young objects that outshine the countless dim ones surrounding them. The real population of the Orion Arm is dominated by stars you can't see without help. Red dwarfs outnumber Sun-like stars roughly 10 to 1 in the Milky Way. The same ratio holds in the Arm. For every Sun-like star you can point to in the sky, there are roughly 10 dim red dwarfs sitting near it that are completely invisible to you without a telescope. The Arm is full of these quiet, dim, long-lived stars. Some of them are billions of years older than our Sun. Some of them have been burning since the early universe, when the Milky Way itself was young and its structure was still taking shape. They're so conservative with their fuel that some will still be burning long after the Sun has completed its entire life cycle, expanded into a red giant, shed its outer layers, and cooled into a dark remnant. The dimmest red dwarfs may burn for trillions of years. Long after the universe is many times its current age. The interstellar medium within the Orion Arm is not empty space. Between the stars, between the molecular clouds, in the gaps that look featureless from any distance, there is material, gas and dust, at densities that vary enormously from place to place, but average roughly 1 atom per cubic centimeter throughout the disk of the galaxy. That is extraordinarily thin by any human standard. The best vacuum achievable in a laboratory on Earth still contains roughly 100 million times more atoms per cubic centimeter than the average interstellar medium. But scale changes everything. Across light years of distance, even this thin material adds up to something substantial. The interstellar gas is mostly hydrogen, about 74% by mass, with helium making up roughly 24%. The remaining 2%, the trace, is everything else. Carbon, oxygen, nitrogen, silicon, iron, calcium, sulfur, and dozens of other elements in various ionization states and chemical combinations. That final 2% is called the metals in astronomical terminology, a usage that confuses chemists who define metals more specifically. But in astronomy, anything heavier than helium qualifies. The dust mixed into this gas consists of microscopic solid particles, typically less than 1 micrometer in diameter, made of silicates, carbon compounds, and various ices. These dust grains do several things that matter enormously for the long-term behavior of the arm. They block starlight, which is why you can't see through the disk of the Milky Way in visible wavelengths. They provide surfaces where atoms can meet and stick together, enabling the formation of molecular hydrogen and more complex molecules that couldn't form in the gas phase. They absorb ultraviolet radiation from nearby stars and re-emit it as infrared, redistributing energy through the medium. And they're the raw seeds around which more complex chemistry builds up in the coldest, densest regions of molecular clouds. When a cloud collapses to form stars, those dust grains end up in the protoplanetary disk. They collide and stick together, grow from micrometers to millimeters, to centimeters to meters, to kilometers, slowly building the planetesimals that eventually become planets. Every rocky planet, including Earth, was built largely from material that was once interstellar dust grains, drifting quietly through the interstellar medium of the arm. The silicon and oxygen in the rocks beneath your feet were once microscopic grains floating through the space between stars. The iron in your blood was forged inside a massive star that lived and ended its life before our sun existed, scattered through the arm by a supernova explosion, and eventually swept up into the cloud that formed the solar system. The carbon in every molecule of every cell in your body went through cycles of stellar nucleosynthesis and interstellar chemistry before ending up as part of a living organism on a planet embedded in this arm of this galaxy. The arm isn't the background to our existence. In a very direct material sense, the arm is what we're made of. Let's look at what's happening inside the arm at this moment. Not the static picture of stars in their current positions, but the dynamic reality of a structure in ongoing motion and transformation. Stars in the Orion Arm are moving. Not just orbiting the galactic center together, but drifting relative to each other in all directions. The Sun is moving through the local stellar neighborhood at about 12 miles per second relative to the average motion of the nearby stars. This is called the solar apex motion. The direction the Sun is heading, the solar apex, is a point in the constellation Hercules. Over tens of thousands of years, this drift will carry the Sun to a meaningfully different position relative to its current nearest neighbors. Everything else is also moving. Barnard's star, at roughly 6 light-years distance, is crossing our sky faster than any other known star, a property called high proper motion. It's not just moving across the sky, it's also approaching the solar system. In about 10,000 years, it will reach its closest point of about 3.8 light-years from our Sun, temporarily making it the nearest star system to us, briefly displacing Proxima Centauri from that position before it continues moving away. Nearby stars have been closer to us than they are now, and they'll be closer again in the future. The local stellar neighborhood is not a fixed arrangement. It's a constantly shuffling collection of stars drifting past each other on timescales of thousands to millions of years. Stars in the Orion Arm are being born right now. In the molecular clouds of the arm, hydrogen gas is collapsing under its own gravity into new stars. The process takes tens of thousands of years, from the initial collapse of a cloud fragment to a star hot enough to ignite nuclear fusion at its core. In the Orion molecular cloud complex, there are hundreds of protostars in various stages of this process. Some have already switched on nuclear burning. Some are still gathering material from their surrounding envelopes. Some are surrounded by protoplanetary disks where solid material is beginning to clump together. It's possible that Earth-like planets are forming in the Orion Nebula right now. By the time the Sun has run through another billion years of its life, some of those protoplanetary systems will be mature. Stable solar systems, with their own histories, unfolding on their own timescales. Stars in the Orion Arm are also ending their lives. The most massive stars, the ones 10 or 20 or 100 times the Sun's mass, burn through their fuel in millions of years and end in supernovae. A typical large galaxy, like the Milky Way, experiences roughly one supernova every few decades. Most are hidden behind dust and not visible from Earth. But the physics doesn't care whether we can see them. Stars are ending in the arm right now. Stellar remnants are being created. Neutron stars spinning hundreds of times per second, emitting beams of radiation that sweep through space like cosmic lighthouses. Black holes, remnants of the most massive stars, sitting quietly in the interstellar medium, detectable only by their effects on surrounding gas or companion stars. The arm is not a stable, finished structure. It's an ongoing process. Material cycling through generations of stars, from gas to star, to supernova, to enriched gas, to the next generation of stars. That cycle has been running in this part of the galaxy for billions of years. It will continue running long after the Sun is gone. Betelgeuse deserves its own moment here. It's not a distant object. On galactic scales, it's practically next door, about 700 light-years away. In the constellation Orion, it marks the left shoulder of the Hunter, a red supergiant so enormous that if it replaced our Sun, its outer surface would extend past the orbit of Jupiter. Betelgeuse is in the late stages of its life. It's consumed the hydrogen in its core, moved on to helium, and is now burning heavier elements in nested shells around an increasingly dense, iron-rich center. Iron is the endpoint of stellar nucleosynthesis. You can extract energy by fusing elements lighter than iron together. You cannot extract energy by fusing iron. When a massive star builds an iron core, the core collapses. The collapse is so rapid and so energetic that the outer layers of the star are blasted away in a supernova. Betelgeuse is moving toward that moment. How soon is not known precisely. It could be in 10,000 years. It could be in 100,000 years. It could, in principle, be sooner. The star fluctuates in brightness irregularly, a sign of the instability that characterizes massive stars in their final phases. In December 2019 and January 2020, Betelgeuse underwent a dramatic dimming event, fading to roughly 40% of its typical brightness. For a few weeks, it was dimmer than it had been in the modern era of careful astronomical observation. Speculation was immediate and widespread. Was it about to go supernova? It wasn't. The dimming was caused by a large mass ejection event in which the star expelled a substantial cloud of gas that then cooled and condensed into dust, temporarily obscuring the star's surface from our view. Betelgeuse recovered its brightness as the dust dispersed. But the episode revealed just how dynamic and unpredictable these massive stars are in their final phases of evolution. When Betelgeuse does finally go supernova, the event will be visible in daylight from Earth. It will cast shadows at night. It will appear as bright as the crescent moon. It will be, without any question, the most dramatic astronomical event in recorded human history. And it will be a feature of the Orion Arm. The death of a star that has been part of the Arm's stellar population for about 8 to 8.5 million years. Its core will be left behind as a neutron star, compressed into a sphere roughly 12 miles across, denser than an atomic nucleus, spinning rapidly and cooling slowly over billions of years. The outer layers will expand outward, creating a glowing supernova remnant that will be visible for thousands of years as it sweeps through the interstellar medium around it. Eventually, that material will mix back into the Arm's interstellar medium, enriched with the elements Betelgeuse produced during its life. Those elements will become part of the next generation of gas clouds, part of the next generation of stars, part of the next generation of solar systems. And the cycle continues. This cycle of stellar birth and death is not just a process happening around us. It's the process that made us possible. The Sun is a third-generation star, or possibly later. That designation means the gas from which it formed had already been processed through at least 2 previous generations of stars before being incorporated into our solar system. The first stars in the universe, sometimes called population 3 stars, formed from almost pure hydrogen and helium. There were no heavier elements. No carbon, no oxygen, no iron. Just the 2 lightest elements produced in the first few minutes after the Big Bang. Those first stars were likely enormously massive, far larger than any stars we see today, because the gas they formed from had no metals to cool it efficiently. And cooling is what allows gas clouds to fragment into smaller pieces. Without efficient cooling, the gas clouds collapsed into huge, massive stars that burned through their fuel rapidly and ended in supernovae within just a few million years. Those explosions scattered the first heavy elements into the universe. Carbon, oxygen, neon, silicon, iron, everything up through the Iron Peak, forged in the cores and expelled in the deaths of those first stellar generations. A second generation of stars formed from gas now enriched with these metals. Some of those stars also ended in supernovae, further enriching the interstellar medium. And so on, through multiple generations of stellar birth and death, each one adding to the reservoir of heavy elements available for subsequent stars and planets. By the time the Sun formed 4.6 billion years ago, the interstellar medium, in its part of the Orion Arm, had been processed through enough stellar generations that it contained roughly 2% heavy elements by mass. That was enough to build rocky planets. The Earth, Venus, Mars, Mercury, all the terrestrial planets in our solar system, were assembled from material that exists because of billions of years of stellar nucleosynthesis in this arm. If the Sun had formed earlier, in a less processed environment, the raw material for rocky planets might not have been available. If the Sun had formed too late, some of the remaining star-forming gas in the arm might have been used up. The timing and location of the Sun's formation within the arm matters. Not in a designed way, but in a physical, consequential way that traces back through multiple generations of stellar history. Positioning ourselves on a map of the Milky Way is one thing. Actually grasping what the numbers mean requires something more. Let's try to get at it from a different direction. The fastest human-made object in the history of spaceflight was the Helios 2 solar probe, which, at its closest approach to the Sun, reached speeds of about 157,000 miles per hour, driven by the Sun's gravity as it swooped inward. This remains the speed record for anything we've built. At that velocity, traveling from Earth to the Moon would take less than 2 hours. Traveling from Earth to the Sun would take about 25 days. Traveling to Pluto, at its average distance from the Sun, would take roughly 2.5 years. Now, take that speed and point it at the nearest star. At 157,000 miles per hour, reaching Proxima Centauri would take about 19,000 years. 19,000 years. The first permanent human settlements hadn't appeared yet 19,000 years ago. There was no agriculture, no writing, no cities, no metal tools. The last glacial maximum had just ended. A probe launched at that moment, at the fastest speed any human object has ever achieved, would still be traveling through interstellar space right now. It wouldn't have arrived yet. And Proxima Centauri is the closest star we know of. The Orion Arm extends thousands of times farther than that. The arm is not a place we are going to cross. It's not a place we are going to explore in the way we explore a continent. It is simply the context of our existence, vast beyond any practical meaning of that word, and we are embedded in one small, quiet corner of it. What's remarkable is not that we're small. What's remarkable is that we know any of this. The question of whether the Orion Arm hosts other life is, in many ways, the most important question embedded in everything we've covered. The arm contains billions of stars. Around most of those stars, we now know from the Kepler Space Telescope survey and subsequent missions, there are planets. Kepler surveyed a sample of roughly 150,000 stars and found that planet formation is not rare. It appears to be the default outcome of star formation. Most stars have planets. The fraction of Sun-like stars with rocky planets in the approximate habitable zone is estimated somewhere between 10 and 40%, depending on the specific definition of habitable zone and which stellar types are included in the calculation. Even at the lowest end of that estimate, the number of potentially habitable rocky worlds in the Orion Arm alone is enormous. Hundreds of millions, at minimum. Possibly billions. That doesn't mean they all have life. We have exactly one data point for the emergence of life, and we don't fully understand how it happened even on our own planet. The chemistry of the first cell, the path from complex organic molecules to self-replicating systems, is still one of the deepest unsolved problems in science. The origin of life may require conditions far more specific than simply having a rocky planet with liquid water. Or it may be robust enough to emerge under a wide range of circumstances. We don't know. But the sheer number of candidate worlds within just this one arm of just this one galaxy means that even if the probability of life emerging on any given habitable world is extremely small, the expected number of worlds in the arm where life has emerged is still potentially substantial. The search for signatures of biology in the atmospheres of nearby exoplanets is underway and accelerating. The James Webb Space Telescope is analyzing the atmospheric chemistry of rocky planets orbiting nearby stars, looking for combinations of molecules that would be difficult to explain without a biological source. Oxygen, combined with methane, is one such signature. In a world without biology, these two gases react with each other and don't accumulate. Their simultaneous presence in an atmosphere requires something continuously replenishing them against chemical equilibrium. Life is the obvious candidate. The TRAPPIST-1 system, about 40 light-years from Earth, is comfortably within the Orion Arm and has attracted intense scientific attention since its discovery. It contains 7 rocky planets, 3 of which orbit in the habitable zone of their central red dwarf star. TRAPPIST-1 is a red dwarf, so cool and dim that its habitable zone lies extremely close in. The planets there are tidally locked, with one hemisphere permanently facing the star and the other in permanent darkness. The red dwarf also produces frequent, intense flares. Whether those conditions support or suppress life, whether the radiation environment is too harsh for surface biology but potentially hospitable in the oceans of tidally locked worlds, whether the lack of a day-night cycle makes complex climate dynamics impossible or merely different, are all active research questions. We don't have the answers. We are building the instruments and accumulating the data that might eventually provide them. Within the next decade or two, barring catastrophic disruption to scientific infrastructure, we will have the first genuinely informative observations of rocky exoplanet atmospheres. The answer to whether we're alone in the Orion Arm may not be far off. And either answer will be the most significant scientific result in history. Finding evidence of life elsewhere in the Arm would transform everything we think we understand about our place in the universe. Finding that the Arm is otherwise empty, despite billions of candidate worlds, would raise questions about the nature of life and its emergence that would drive science for generations. Neither outcome is quiet. There's another way to understand our position in the Orion Arm that doesn't involve distances or luminosities. It involves time. The Arm has existed, in roughly its current form, for hundreds of millions of years. Our solar system has been part of it for about 4.6 billion years. Life on Earth has existed for at least 3.8 billion years. Complex, multicellular life has existed for roughly 540 million years. Our genus, Homo, appeared roughly 2 to 3 million years ago. Modern humans, our specific species, appeared roughly 300,000 years ago. The first written records we have extend back about 5 to 6,000 years. We have been doing modern science with careful observation, measurement, mathematics, and the systematic testing of ideas for perhaps 500 years, depending on where you draw the line. We have been doing astronomy, capable of reaching beyond the nearest stars for roughly a century. We have been doing astrometry, capable of mapping the Orion Arm's actual structure for perhaps 30 years. The Gaia mission, which has done more to reveal the Arm's true extent than anything before it, is still operating. Its most detailed data releases are still being analyzed. The picture we have of the Orion Arm in the year 2026 is the most accurate picture that has ever existed, and it's still incomplete. We are at the very beginning of understanding the structure we live in. The Arm has been here for far longer than our species has existed. It will be here for far longer than our species is likely to exist. And we have been looking at it carefully for a time so small that it barely registers against the arm's own history. A few decades of precise astrometry. A few decades of infrared and radio mapping against hundreds of millions of years of the arm's own existence. And yet, in those few decades, we've gone from thinking we lived in a minor spur to understanding we live in a substantial galactic structure, tens of thousands of light years long, filled with billions of stars, containing countless regions of active star formation, hosting billions of candidate worlds, shaped by supernova events millions of years before our species appeared, and sitting inside a bubble those ancient explosions created. That's the pace of what we're doing. That's what a century of careful looking has revealed. Imagine what the next century brings. There are places inside the Orion Arm we know almost nothing about. Not because they're particularly distant. Some of them are only a few thousand light years away. But they're embedded in regions where the dust is thick enough to block visible light almost completely, making observation in optical wavelengths nearly impossible. The galactic plane, in the direction of the center, is one such region. Towards Sagittarius and Scorpius, the interstellar dust lanes are so dense that visible light from objects more than a few thousand light years away is absorbed almost entirely. To see into those regions, you need radio telescopes, infrared telescopes, or X-ray observatories, each of which penetrates dust differently and reveals different populations of objects. The ALMA Observatory, the Atacama Large Millimeter Array in Chile, is particularly powerful in this regard. ALMA observes at millimeter and sub-millimeter wavelengths, which penetrate dust effectively and reveal the cold, dense molecular gas in star-forming regions. It has imaged protoplanetary disks around forming stars in stunning detail, including disks with gap structures that suggest planets are already forming within them. It has detected complex organic molecules in molecular clouds, including compounds that are building blocks of the chemistry of life. Not evidence of life. Evidence that the raw materials of life's chemistry are distributed through the arm's molecular clouds. This is a significant distinction that matters a great deal. Amino acids, the building blocks of proteins, have been detected in meteorites that fell to Earth. They've been detected spectroscopically in molecular clouds. They form readily in laboratory experiments, simulating interstellar conditions. The molecular complexity needed to get from raw elements to life is not the hard part. The chemistry happens readily, under a wide range of conditions. What we don't understand is the transition from complex chemistry to self-replicating biological systems. That transition, wherever it happened on Earth, and however long it took, is the gap we can't yet bridge in our understanding. But the arm is full of the ingredients. The question of assembly is the one we don't have the answer to. There's a final aspect of the Orion Arm that matters and that rarely gets discussed. Our position in the arm relative to the galactic plane. The Milky Way's disk is not perfectly flat. It has a slight warp, a gentle bending that becomes more pronounced toward the outer edges of the galaxy. Within the disk, individual stars, star clusters, and molecular clouds sit at different heights above and below the theoretical midplane. The Sun is currently located very close to the midplane, slightly above it by roughly 80 light-years, which is negligible on the scale of the disk's full thickness of several hundred to 1,000 light-years. But the Sun oscillates up and down through the galactic plane over time. The period of this oscillation is roughly 60 to 70 million years. The Sun bobs up above the midplane, slows, reverses, passes back through, goes below, and returns. At its maximum excursion, it reaches a few hundred light-years above or below the midplane. During the parts of this cycle where the Sun is near the midplane, it's in the densest region of the disk, with the highest concentration of stars, gas, and dust. During the parts where it's furthest from the midplane, it's in a thinner, less dense environment. This oscillation has been proposed as another factor in the long-term history of life on Earth. When the solar system is near the midplane, it passes through more dense material, potentially triggering more gravitational perturbations of the Oort cloud and sending more comets toward the inner solar system. Whether this translates into measurable patterns in impact rates or extinction events is debated and not clearly established in the geological record. But the fact that our position in the arm is three-dimensional, not just a point on a two-dimensional map, and that this position changes over time in multiple ways, is part of the full picture of where we are and what that means for the history of our planet. We are not fixed in place. We're moving in three dimensions relative to the structure around us, through a dense and active part of the galaxy, oscillating through the midplane, slowly drifting relative to our stellar neighbors, making one slow circuit of the galactic center every 225 million years. Everything is in motion. The Orion Arm is not a container we sit still inside. It's a dynamic structure we're moving through, and the details of that motion have had real consequences for the world we inhabit. The Gaia satellite is still collecting data. It will continue refining its map of the Milky Way's stellar population for years to come. Each successive data release has sharpened the picture. The third major release, in 2022, was transformative. The fourth, when it comes, will be more so. New radio telescope arrays are mapping the Milky Way in radio wavelengths with resolution that would have been inconceivable a generation ago. The Square Kilometre Array, an international project that will eventually link thousands of individual radio dish receivers across South Africa and Australia, will have the sensitivity to detect signals from across the galaxy that current instruments cannot reach. The next generation of extremely large optical telescopes, ground-based mirrors 30 to 40 meters in